So here I have four different species that I would like us to take a look at in terms of determining what the oxidation states or oxidation numbers are of each of the elements in each of the compounds or ions. So if you want to take a pause here and try and work through those, I'll come back. Alright, welcome back. And what we see here on our first compound, sulfurous acid, H2SO3, we can pretty easily decide here what the charges of the hydrogen and oxygen are, because we can use rule number 5. And we said in rule number 5 that oxygen is usually a -2 and that hydrogen is usually a +1. There are 3 oxygens, and so that gives us a grand total of -6, and we have a grand total of 2 hydrogens for a total of +2 charge. All of this has to equal 0 because there is no charge up here whatsoever, right? And so whatever +2 plus something -6 is has to equal 0, and that something then must be a +4. So that tells us that the charge of the sulfur is a +4. Moving on to the sulfuryl chloride, here we have the most electronegative element being oxygen. Oxygen is a -2. The chlorine is not always as easy as this, but this chlorine is more electronegative than the sulfur is, and so the chlorine is a -1. That gives us a grand total of -2 for the oxygen, -2 for the chlorine, and again there is no charge on this compound, so it has to equal 0. Therefore the charge on the sulfur must be a +4, right? So sulfur gets a charge of +4 in this compound. The next ion is a little different because we don't have a charge of 0 on this. We have a charge of -1. So when all is said and done, the total charge must equal the charge on the ion. And again, the oxygen is the most electronegative, so it gets a -2. That's a grand total of -8. And so if we take a look at the manganese, then the manganese must be a +7. And that should make some sense. If you have a periodic table at all available to you, you'll notice that if the manganese were to lose 7 electrons, that we would end up with the manganese being in the noble gas electron configuration at that point. So +7 charge for manganese is actually a somewhat common charge for that. Alright, now the most difficult one here is this very last one. And so this can be done in a number of ways. But one of the things that we must recognize here is that the ammonium is a +1 charged ion. And again, you know that because we memorized that way back when we did the polyatomic ions. So the charge on the ammonium must be a +1. And what does that make the charge of the Cr2O7 portion of the molecule? That makes the charge on this piece of it a -2, right? So we can attack this in 2 different ways. Let's start with what I think is the easier one, and that is the dichromate part, right? So each oxygen is a -2. That gives us a grand total of -14, and the charge on this dichromate is a -2. That means that the chromium must be a total of +12, and since there are 2 chromiums, each chromium must be a +6. Over for the ammonium piece, we recognize that each hydrogen is a +1, and there are 4 of them. So we get a +4 here, and all of this has to equal a charge of +1, right? And so that means that each nitrogen must be a -3. So that should make some sense. Nitrogen being a -3 would make it look like neon for a noble gas. And if we take a look at chromium +6, that also is going to have, I believe, an argon electron configuration, I believe.